So the other day I posted a very long video with several different parts that are unrelated to each other except in the context of what that video is doing. But I do understand that a lot of people don't want to sit through 1 hour of video. So if you only have 20 minutes to spare, then this is the part that I want you to watch. This is not an introduction to complex numbers. You do need to know things about complex numbers in order to understand this video, but it's a very interesting and useful observation about them. And later, if you feel curious to know in what context I was talking about this in the original video, then you can just go to the longer one that is also linked in the description here, and then you can just watch the rest of it. And also, if you stay until the end of this video, I will be solving a question from this year's exam. That's May 2024. And that's not even in the other video. So that's extra content in here as well. I need to tell you about something very important, which is called the roots of unity. And this is a complex numbers thing. I am not sure to what extent this is technically something that we should mention in the syllabus of the IB course, but I do like to mention it because it is so important and it comes up a lot. Now, unity, of course, means one, and root is like a square root, except it doesn't have to be a square root. It can be any index root. And now you're thinking, wow, this is stupid because the square root of 1 is just 1. What else is there to talk about? And in the real numbers, you would be pretty much correct. But the thing is that this is a complex numbers thing. So when I say unity, I mean the number 1, so it's specifically this point here in the complex plane, but I will be interested in looking at the whole unit circle there. In the real numbers, when we say the square root of 4, for example, that's just 2, right? We just mean the positive one. It's a mistake to say that the square root of 4 is plus or minus 2. That's not the technical meaning of the square root. That's why in the quadratic formula, we have the plus or minus in front of the square root, right? So that you can account for both the plus and the minus. It's not inside of the root itself. So it is a different thing to say that the nth root of y is equal to x, or to ask for the solutions of the equation y equals x to the power of n. And it is a lot more in this sense that we are going to talk about the roots of unity. I am interested in what complex numbers to the power of n are equal to 1. Of course, 1 to the power of n is always going to be equal to 1, no matter the value of the n that you are using. But for example, if n is 2, you already know that there is another one, because negative 1 to the power of 2 is also equal to 1. So for n equals 2, you would have this one as another root of unity. 4 as well, in fact, any even number. But when you do 4, you also have I to the power of 4 is 1, and negative I to the power of 4 is also 1. And you see that when you think of multiplication in complex numbers as rotation, which is a very important way for you to think of multiplication of complex numbers. You have to be thinking of the complex numbers in their polar form, so that when you multiply two numbers, well, the modulus is just going to multiply one by the other, right? So r times s. But the arguments, which in this case are theta and alpha, they are going to add to each other. And when you have a point in the complex plane, which is theta, and you're going to add another alpha to the argument of that complex number, that is a rotation. That is rotating by the angle alpha. So you have to be thinking of that in terms of rotation. And of course, the modulus can change as well if you're multiplying it by s, but that's not important. I want to talk about the angles because all of my examples here are going to have modulus 1. I am in the unit circle. I'm looking for the roots of unity. So this one up here, which is the number I, it has started here and went 90 degrees. So if you put it to the power of 4, it's 90, 90, 90, 90, and it's back where it started. This one here, which is the number negative 1, is going to be 1, 2, 3, 4. So it went around twice in the unit circle, but it also got back to where it started. And finally, negative I is going to do the exact same. You could think about it rotating the other way, but I don't want to do that. I want to think that negative I just has this argument, and I'm going to put it to the power of 4. So I need to rotate it another 1, 2, and 3. So it went around even more, but it got back to the same place. So these are the fourth roots of unity. 1 itself, I, negative 1, and negative I. I'm going to do another example with the cubic roots, but they all work exactly the same. So if you are looking for something that to the power of 3 gets back to the same place, it can either be the number 1, which is always going to be one of the roots, and it doesn't go around the circle at all, right? It just stays there. But if your original number z is just 1/3 of the way around the circle, therefore 120 degrees here, then when you take this z to the power of 3, it's going to get back to the number 1, because 1, 2, and 3. So this one here is z squared. And it's also one of the roots of unity, because if you started by going 240 degrees, then another 240, and another 240, you went around the circle twice, but you got back to the same place, so you are also a root of unity. Writing this number in polar form is super convenient, and if you know your trigonometry well, you can also write it in Cartesian form if you want, but I am not really sure why you would do that. And this other root of unity here is with 4 pi over 3, and its coordinates are this. But the moral of the story is that the roots of unity are always equally spaced around a circle. So if you want the 8th roots of unity, you take your circle, you cut it into 8 equal pieces, and those points are going to be the roots of unity. 8 is a particularly easy number to draw, but it could be any number. 5 is very difficult to draw, but I tried it anyway. So here are the 5 roots of unity. These are the numbers that when you put them to the power of 5, the answer is 1. And then if you want to have a number that to the power of 5 is equal to 2 or something else, it's not going to be in the unit circle, but then you just treat the modulus separately. Then the numbers that to the power of 5 are equal to 2 are not these ones that are marked here, which are z, z squared, and so on, but they are going to be the 5th root of 2 times z, and then times z squared and z cubed, and so on, because you treat the modulus separately, and the modulus is just a real number, so the 5th root of 2 is just the 5th root of 2. So I'm not going to talk about numbers outside of the unit circle anymore, because the modulus is very easy to handle in case you need it. But this is also useful to get roots of numbers that are not 1. So maybe what if you want the cubic roots of I, for example. So now you're looking for numbers such that z to the power of 3 is I. Well, there is one in the first quadrant that you can find just by splitting the first quadrant into 3 equal pieces like you usually do. And this is just going to be 30 degrees right here. That is your first number such that z to the power of 3 is I. But now, if you want the other two, you don't need to calculate anything. You just need to rotate this one 120 degrees and then another 120 degrees, because it will be the same picture as we were just drawing for the roots of unity. So 120 plus 30 is 150, which in this case is going to bring me exactly to the other side of the unit circle. And then this one, well, I don't want to call it z squared this time because it's not the square of the first one, but I'm going to call it w. And then another 120 degrees later, we are coincidentally right here. And this third answer is just negative I, which if you think about it, yeah, negative I to the power of 3 is equal to I, right? So there you go. Easy way to solve any equation of the form z to the power of n equals some number. Anytime that you want to solve an equation like this, just know that it is very easy. You don't have to calculate anything. This is just one of those bits of knowledge that you bring with you and you apply it, but you don't have to think about it over and over again because we are already doing the thinking right now. And k here can be any complex number, okay? So first of all, you look at the size of k, you look at the modulus. If it's not 1, then you keep that information for later because you are going to need to put modulus in your answers as well. But other than that, you just put your number k wherever it is. You look for its argument. You take the argument divided by n, which is the power that you want, right? To find your first answer. And then for the other answers, you just split this circle into n equal parts, and that's it. So this comes up a lot in ways that I sometimes find surprising. This is an example that I like a lot. So look, we have 13 marks here to start this question. This was not the whole question. The whole question was actually, I think, 22 marks. It was really big. It was a question 12 of an exam, which is supposed to be the most difficult one. But look how easy we are going to get these 13 marks. The equation that we want to solve is z minus 1 cubed equals I. So it's almost the same as we were just talking about, something to the power of n equals k, but we have this minus 1 now, which is a little bit different. So I am going to start by letting t equals z minus 1. I'm not using w because he is using w in the question and I don't want to get mixed up. And I know that t is a weird name for a complex number, but whatever. So what I want to do is to solve t to the power of 3 equals I, which is an equation that I solve immediately. The first answer is e to the I pi over 6, because this is 30 degrees, 60, 90 to get to I. And then I add 120 to that. I get this other solution here, which is e to the I 5 pi over 6, and adding another 120, I get my final solution, which is this one. This I'm just going to call minus I. But these are values of t, and t was z minus 1. So the values of z were t plus 1, which means that I need to take these 3 red points and shift them 1 to the right. So I shifted the whole unit circle here to the right, and I drew it in green. And now I'm going to bring my points here, here, and here. So these 3 blue points are the solutions to my original equation. Z minus 1 to the power of 3 is equal to I. Now that I've done that, let's see what the question wants me to do. AI, verify that 1 plus e to the, oh, we can't really read that. It's e to the I pi over 6. Verify that that is a root of the equation. Well, yeah, that is the first blue point there. That is a root of the equation. Find W2 and W3, expressing them in that form. Okay, so W2 is going to be 1 plus e to the I 5 pi over 6, which is that other point over there. And W3 is going to be the final one down here, which is 1 minus I. And I know which one is which because the question told me that the imaginary part of W2 was bigger than 0, so it's not possible for the bottom one to be W2. Oh, but he doesn't want me to write it as 1 minus I, does he? He wants me to write in this form. Okay, 3 pi over 2. There you go. Now, the roots W1, W2, and W3 are represented by the points A, B, and C respectively. Oh, okay. So let's call the points in the diagram as A, B, and C. Plot the points in an Argand diagram. Okay, I've already done that. And now find AC, the distance between these 2 points. Well, that is a little bit of geometry, isn't it? The point C has coordinates 1 and -1, and the point A has coordinates 1. Where's the half? The half is the y coordinate, and then so this is 1 plus root 3 over 2. So now I just want to find the distance between these 2 points, and you can use the formula for distance between 2 points. 13 marks in a question 12. We did this in seconds. The 1 here that we were shifting to the right, the 1 is this point here, which is the average of the roots of the equation. It is in the middle of all 3 points, equally spaced around the circle, so that is the average of the location of the 3 points. So when I was editing the video, I decided to include an extra comment here because it occurred to me that I'm not sure if it's obvious that the point in the center of the circle is actually the average of all the roots of unity around it. And I think it is kind of obvious for even numbers because you can do by pairs. So this pair, this and this, the average between them is clearly the point in the middle, as is the average between these 2 points. And if you were doing the average of a bigger number like 8, you can still think of the opposite pairs, right? The average between this point and that point over there is clearly the midpoint in the middle, which it all ends up being the center of the circle. Maybe it's not so obvious for odd numbers though. So there is a little argument that I can try to use to convince you that the point in the center actually is the average of all the 5 points. And it's also about trying to put them in pairs because this horizontal line is the real numbers and the vertical line is the imaginary part of the complex numbers that we are dealing with. So that number is a real number, which is the number 1. And these two are conjugates of each other. These two on this side are also conjugates of each other. So when you add up all 5 points, at least you know that the imaginary parts are going to cancel out. So maybe that is not enough to say that 0 is the average of all 5 points, but at least it's a real number because the imaginary part of this one is canceling out the imaginary part of this one, and the same from that pair over there. So the average is going to have to be a real number somewhere in this horizontal line here. But now if you rotate yourself a little bit, and instead of looking at a horizontal axis or a vertical axis, you decide to look at this sort of diagonal axis here that is lined up with one of the roots of unity, and it can be any one of them, but I chose this one. So now you can take the other 4 points and put them in pairs across this axis as well. This is no longer about imaginary parts canceling out because the imaginary part is still vertical. But when you think of the midpoint between these 2 points, which is the average of the 2 points, then it is someone in the blue axis, and the midpoint of these two is also in the blue axis. This point is also in the blue axis. So when you take the average of everybody, it needs to be a point in the blue axis. But we had already mentioned before in the previous picture that it also needed to be a point in the horizontal axis. And the only point that does both of those things at the same time is 0. So that's how I know that the average of all the points equally spaced around the circle is actually in the middle of the circle. And in fact, I didn't even realize this before I posted the other video, so I didn't include it there. But question 12 from paper 1 in this year, you can pretty much solve everything on it, if not with the exact same things that we were just talking about, then with very similar ideas. So the whole question is 20 marks. I'm going to try to talk you through the whole thing. And I'm going to start in maybe a little bit disappointing way because question A is asking us to find the real part and imaginary part of this number to the power of 3. This just feels like something I don't want to do. So I'm going to skip it. I'm not going to do it. I don't need those 3 marks. I'm going to be fighting for 17. Because part B is hence or otherwise. And although I always say that 99% of the time where he says hence or otherwise, he actually really means hence. This is one of those rare occasions where I'm going to ignore the hence and I'm going to choose the otherwise, because I don't want to do this in Cartesian form. I don't care that the real part of it is something and the imaginary part is something else. I want to work in polar form, and I have very good reasons for this choice, and that's why I'm skipping the hence. 1 plus root 3i is here. This is not the unit circle. This is a circle of radius 2. And the reason why I know this is because I recognize the numbers 1 and square root of 3 as the numbers in the legs of my special triangle. So I also know that this angle here is pi over 3. I know that the hypotenuse is 2, which is the radius of the circle I'm working with. So the thing he is asking me to show is obvious, because when I put this to the power of 3 and I'm thinking of this as rotation, this is pi over 3, 2 pi over 3 pi. If this was the unit circle, we would be falling right over there in -1, but it's not the unit circle, the radius is 2. So as well as doing this rotation that puts us on the left side of the horizontal axis, we're also multiplying the modulus by 2. So it's 2, 4, 8, so the answer is -8. In part C, he decides to look for the other roots of the equation z cubed equals -8, which is the same equation that he just gave us one of the solutions to. He says that this one is called u. He also says that v is a real number, and he asks us to give v and w. He does say specifically in Cartesian form, which may sound like something I wouldn't like to do because I obviously like working in polar form, but because the numbers are these, square root of 3, and the same numbers as usual, you will see that it's going to be an easy thing to do. So the thing that we were just talking about, equations of this type, z to the power of n equals k, is that once you have one of the solutions, all that you need to do to find the others is to split the whole circle into, in this case, 3 parts, because n is 3. So I am going to put the other one here and the other one here. The angle between two red things here is always 120 degrees because I'm splitting the circle in 3 parts. V is a real number just like he wanted. V needs to be the number -2 because that needs to be the modulus, so that when you put it to the power of 3, the modulus becomes 8. And W is just this one, that is the conjugate of U. There were other ways of thinking about this, of course. You could have found the -2, obviously, because -2 to the power of 3 is -8. And then you could have remembered that in polynomial equations, once you have one solution, then the complex conjugate of that solution also needs to be another solution. But I don't like thinking about polynomials. I like complex numbers a lot more. In part D, he asks us for the area of the green triangle here, and I'm not going to do it just because it doesn't relate to what I want to talk about in the video, but if I was a student taking the test, I wouldn't skip this question. I would actually do it. So here comes the really interesting part. In part E, he asks us to take these 3 points that we already have and to rotate them by pi over 4. We're going to be rotating counterclockwise, and I'll make an effort to make my sketch look precise enough so that I can understand what's going on with these points. And this is interesting because pi over 4 is also the same number as it always is. We're always working with these two numbers, but we are not always working with them together in the same problem, pi over 3 and pi over 4. So the thing that you should be careful with in the precision of your sketch is that pi over 4 is not that difficult to draw in itself. It is the precise middle of each one of the quadrants, but just make sure that it looks correct relative to the pi over 3, because pi over 3 is bigger than pi over 4. Not by much, but it's bigger. That's why these two look kind of close together. So rotating v by pi over 4 is going to be the easiest one because it's already aligned with an axis. So when I rotated pi over 4, it's going to come here. That is the point that we're supposed to call v prime, the rotation of v. And he asks for the point in polar form. So 2 is the modulus. And for the argument, I went with -3 pi over 4 going this way because he said that he wants it between minus pi and pi. So now let's do the other ones. W was a little bit behind this green one, and the next green one is the horizontal one. So W prime is going to be a little bit before that. The modulus is 2, like all the other ones. And the negative pi over 12 there, well, that's just negative pi over 3 plus pi over 4. It's just adding two fractions. And the u was a little bit after this one, so it's going to be a little bit after the vertical. This is 6 pi over 12, so 7 pi over 12. And now, just between us, because he didn't really ask anything about that, but the three red numbers here were spaced with 120 degrees between each other, and they all suffered the same rotation to make the green points. So the green points also are separated by 120 from each other, which makes them perfect to be the three solutions of z cubed equals something, because that's what we were just talking about throughout the rest of the video. And if you want to figure out what the something would have to be, you just have to take one of them and put it to the power of 3 to see where it goes, because you know that the other ones, because they are in a circle spaced out evenly, then they will have the same cube, because that's how roots of unity work. So let's take this one. It seems like the easiest one. So if you put that to the power of 3, the modulus is going to be 8, of course, and the argument is going to be negative 3 pi over 12, which is negative pi over 4. I'm changing my notation here for the orange points. I'm just pointing out the angle that they are, because I'm not actually interested in those points in the circle of radius 2. Just put them there because I wanted to see the angles. So that's like 1, 2, 3. That's why this point would be the cube of that. And that's the information that we've just extracted from the picture, that u prime, v prime, and w prime, the green points here, are roots of the equation z to the power of 3 is equal to 8 e to the minus I pi over 4. And I've called that part F because this is exactly what part F is asking us to do. Given that u prime, v prime, and w prime are the solutions of z cubed equals c plus di, find the value of c and the value of d. The only difference between what he asked me to do and what I've already done is that I gave the answer in polar form, and he wants the answer in Cartesian form. But again, because this is pi over 4, it is one of my special angles, this transformation is very easy to do. In the unit circle, this would be root 2 over 2, but that's multiplied by 8, so that is 4 root 2. And the imaginary part is the same, but it's negative because of the quadrant where it's at. Only one part left to go in this question 12, and it's part G. It goes like this. Given that u, v, w, u prime, v prime, and w prime, so all 6 points together, are all solutions of z to the power of n equals alpha, for some complex number alpha and for some natural number n. But there is an important interpretation thing to talk about here. When he says these 6 points are all solutions of this equation, he doesn't mean that they are all of the solutions. He means that all of these points are solutions. So he said this sentence in a very ambiguous way, which I don't particularly like. He said that u, v, w, u prime, v prime, w prime are all solutions of z to the power of n equals alpha. Now, this can be interpreted in both ways, that these 6 points are all of the solutions to that equation, or that all of these points are solutions to that equation, but there might be more solutions that we are not talking about yet. And the only reason that I know that the second interpretation is the correct one is because I know about roots of unity. I know that solutions to this equation need to be equally spaced around a circle. And these 6 points are not. This space between these two is different from the space between this and this. The question is, where are the other solutions? Well, the other solutions are the points that we need to put there in order to make everything equally spaced. So I think that the answer is 12. I think that the smallest value of n that makes this possible is 12. And the answer is going to be to look at the difference between these spaces. Like I said, this space is not the same as this space. So let's see what those spaces are. Between this and this, I have, well, this is 4 pi over 12. and one more. So we have 5 pi over 12 here. And between this and this, well, this is clearly 3 pi over 12, right? We had already done this before because one is a pi over 4 rotation of the other. So pi over 4 is 3 pi over 12. I'm writing it like that because I want it in the same denominator. So yeah, that's the points that you need to put in between, right? You have to put these two orange ones here. You need to put 4 purple points here to make 5 spaces of length pi over 12 each. And it's not possible to do it by putting less than that many points because, first of all, this is not a multiple of this. So if this was twice as big as this, then we could think of just putting one extra point here, here, here. But that's not the case because it's not double. It's almost double. It's 5 and 3. And by just putting 1 point here in the middle of these two instead of 2 points, then we couldn't make it fit over there. So we actually need these 2 points, and then the spaces between each point is going to be pi over 12, therefore n is 12. So he didn't ask for the value of alpha, but again, if you want to find it, all that you need to do is put one of these to the power of 12 and see where it goes. I'm choosing this one again, so the argument, if I put this to the power of 12, is just going to be here. So the answer is that alpha is going to be a negative real number. And as for the modulus, this one was 2 as everybody else. So 2 to the power of 12. That's the equation that he was talking about. And listen, I don't mean to say that this was easy, okay? It's definitely difficult. It's the last part in the last question of a high-level exam. But what I am saying is that even though it's difficult, I was able to do it and to know how to do it because I know about roots of unity. So what I'm saying is that this is important knowledge for you to have.